protons with a gas or a radiation field, and the time scale the protons leave the system. So the charged particles can never be confined forever in an astrophysical source. So if you compare these two time scales, then you can measure what is the efficiency of that process. If the interaction time scale is much, much shorter than the escape time scale from the system, then this quantity goes to unity. So you have the calorimetric, you have a source which is calorimetric in terms of energy transfer from protons to secondary particles. And here's just an example to show you this efficiency factor as a function of the proton energy or proton-Lorentz factor for a typical astrophysical source. And you can see that it can be very, very small, close to the threshold, but it can rise up to a value of 1% or something, depending on the physical conditions of the source. So this is the photopion, this is the production efficiency for neutrinos and other secondary particles. But why is this important? Because instead of doing all these calculations that I showed you in my second lecture, like involving all these four or even more dimensional integrals, we can have a simple formula that relates the energy distribution of relativistic protons in a source with the expected neutrino energy distribution coming out from that source. So this is very simple and very convenient for us to calculate. So on the one hand, we have this parameter. We have this F factor, which is the production efficiency.
For a second, because the slides are not moving on Zoom.
Again, the same problem.
Yeah, there was the same problem. Maybe I have to shut. And now I can share. I'm sorry.
Oh, it's fine.
Maybe if I do like this screen desktop share.
Oh.
Okay, now it's good.
Okay, so yes, we have this very simple formula that relates the proton energy distribution, luminosity here, times this efficiency factor that tells us how much energy is transferred to the neutrinos, and a parameter eta, which is related to the interaction physics. So this part here is related to the acceleration physics that we discussed, how protons are accelerated to high energies. This term here accounts for the interaction physics and the source properties, how big is the source, how dense is the source, and so on. And this is the interaction physics. So it depends on the branching ratio of the interaction, how many charged pions over neutral pions are produced per interaction. So having this very convenient formula, we can actually see or expect how the neutrino spectrum is related to the parent proton spectrum that produces the neutrinos. And here is a sketch for PP collisions. So if you have a power law distribution in protons, like in the cosmic ray proton spectrum is a power law, roughly speaking. If these protons interact with gas, they're going to produce a power law distribution in neutrinos, and the normalization of the neutrino spectrum is going to depend on this efficiency factor for the PP collisions. And you can see it is not depending on anything else. But when we consider interactions of relativistic protons with photons, which are pretty common in astrophysical environments, you can see that the neutrino spectrum has a very different spectrum compared to the parent proton one, because it depends sensitively on the target photon spectrum. So the photon spectra, the radiation fields that we have in different astrophysical sources, they do not always have a universal energy distribution. And this is actually reflected on the expected neutrino spectrum. So this is, let's say, and also in the second exercise, the numerical one, if we have time to discuss it today in the afternoon, you are going to calculate this efficiency parameter for PP collisions, and you are going to numerically compute the neutrino spectrum coming out from an astrophysical source. So this slide will be convenient for later on. So now let's move to the topic of today's lecture, which is extragalactic neutrinos in a multi-messenger context. And what I would like to discuss today is basically to give you a flavor of how we can compute neutrino emission, neutrino predictions from the most promising neutrino sources that we know to date, which are active galaxies. So, quick question. how many of you know about the phenomenology of active galactic nuclei, or what are active galactic nuclei? Okay, not many, so that's good. I have a few introductory slides. So active galactic nuclei, for those who are not familiar, are just a small fraction of the galactic population in the universe. So they comprise about 10% of all the galaxies in the universe, but they are very, very interesting sources because they are high energy emitters. So the active galactic nuclei, oops, I think I did it again. The active galactic nuclei are regions in the centers of galaxies where there is a supermassive black hole which accretes plasma through an accretion disk that you can see here in this artistic impression. And it is also possible to have the launching of a relativistic, collimated, and magnetized plasma outflow. So this is what we call a jet. And just to give you an idea how the jets really look like in real life and not in artistic impressions, here is one of the most famous AGN that have been discovered back in the 60s, 3C273. And you can see here is the host galaxy, which is very, very bright in the optical light, simply because the emission of light coming from this nuclear region of the galaxy overshines the whole galaxy, basically. And this, I mean, back in the 60s, when people discovered AGN, they thought that these are stars, because in the photographic plate, they looked like a star. This is why they were called also quasi-stellar objects. But later on, they, let's say, took spectra from these sources, and they realized that the emission lines that they were finding were not representative of stars. So there might be something else, and they also discovered that this source was at a redshift of 0.1. So back in the day, 0.1 redshift was very high redshift. So this is just to give you the perspective of how things changed also. But anyway, here you can see also in optical light, the jet. You can see it also here with Hubble. And this lies at kiloparsec scales from the center of the galaxy. So one might also ask, why do we see just one jet and not the other one? And this is really important because this jet is moving, this plasma is moving relativistically towards us. So the light that it is being emitted inside the jet is relativistically boosted. So relativistic beaming is super important when we are studying these kind of objects. The other jet, which is moving away from us, the emission is Doppler deboosted, and thereby it's very weak, so you cannot really see the jet. But AGNs have been discovered in optical and radio back in the day, but now we typically discover AGN in the gamma rays. And this is why it is very important to study AGN, because they are the most dominant extragalactic population of high energy emitters in the universe. Here is just the sky map of Fermi-Lat, composed with gamma ray photons with energies above 100 MeV. And you can clearly see this very nice bright galactic plane. But we don't really care about that in this talk. We are interested in all of these point sources, which are extragalactic, and the majority of these sources are AGN with jets, and we call them blazars. What it is also very important to note is that if you take the gamma ray emission, you subtract all the point sources from that emission, you are going to end up with what we call the extragalactic gamma ray background, which is coming or is composed by truly diffuse gamma ray emission from the universe, plus all the other gamma ray sources that are not being resolved because Fermi has a given sensitivity. So if we calculate this extragalactic gamma ray background, and you see here the intensity of that as a function of the gamma ray photon energy, the data are the markers, and there are some estimates here that show calculations that show that blazars, so these AGNs with jets that point towards the observer, towards us, they actually contribute most of this extragalactic background light above 10 GeV. So we kind of know that the dominant sources of high energy radiation, which is being produced by relativistic electrons and positrons, is coming from these jets. But not only that, I mean, blazars also dominate not just the GeV gamma ray sky, but also the TeV gamma ray sky. And this is how, if you look all the red circles here, these are TeV blazars. And I mean, all of these observations were made and discoveries with these Cherenkov telescopes that we have available. But the plan and the hope is actually to augment the number of TeV blazars that we detect with CTAO. And hopefully in the 30s, we are going to have many more detections in order to better understand also the TeV emission of these objects. So going back again to how an AGN looks like, this is a very popular sketch that you might have seen for those who know about, have heard about AGN, but it summarizes more or less the different types of AGN we have. And as you can see, there are many, many different names. I'm not going to go into the details, but broadly speaking, we divide the AGN population in two categories: those that they produce the jets, and these are called radio loud AGN because they have a very high radio emission coming from the jet, and those that they do not have a jet, and they actually are the majority of the AGN. So less than 10% of the AGN population produces a jet, and a smaller fraction of them is what we observe as blazars, just to give you again a sense of what we are discussing. We don't really know why some of the sources are launching a jet and some not. There have been some ideas that they were trying to relate the presence of a jet with the accretion physics. So how fast matter is accreted onto the supermassive black hole, what is the structure of the accretion disk, and as well to relate this process to the strength of magnetic fields present in the accretion flow and how fast the supermassive black hole is spinning in the center. But this is just an idea, but it has not actually been confirmed yet. And how are jets being launched? This is again an open question. We think that in order to launch a jet, what you need is to have poloidal magnetic fields, like magnetic field of large structure that is being rotating together with the accretion disk. The accretion disk rotates differentially, so if you are closer to the supermassive black hole, you are rotating faster. And thereby you can open the magnetic field lines, and then you can imagine like having a spiral, and the spiral becomes more pancake-like. So the magnetic field lines are coming closer and closer together, and they form this kind of toroidal component, which is strong. Okay, that's this Blandford-Snarek mechanism that actually transfers a fraction of the rotational energy of the black hole through electromagnetic fields into much larger distances. So it is an electromagnetically driven jet, if you want. An open question in our field, just to give you again an idea, is that we still don't know how the jets are loaded with plasma. So we are talking about pure electromagnetic radiation, pointing flux that it is being driven away from the center black hole to large distances. But what about particles? How do we create electrons and positrons that we need in order to explain the observations that I discussed before, the optical light, radio, and so on? And additionally, how do we add protons in the jet? Because if we think, and as I'm going to show later, that the associations of blazars with neutrinos are true, then there should be somewhere protons in the jet. So how do we bring protons, where they come probably most likely from the accretion disk, which is ionized plasma, into the jet is an open question. A few things about AGN coronae. This is a component of the AGN, which is directly seen in AGN that they do not possess a jet. So if you see an AGN without a radio loud component, you can see the spectral energy distribution. And the important thing is that we observe directly a power law in X-rays. So this non-thermal X-ray emission is thought to be coming from Comptonization of low energy photons from the accretion disk by relativistic electrons and positrons somewhere in the vicinity of the black hole. Artistic sketch here. Again, this X-ray emission and the presence of the corona in AGN has been discovered in the late 80s, and the first models about what is a corona of an AGN have been proposed in the 90s. But still, there are many, many open questions. For example, what energizes the electrons in the vicinity of the black hole? How are these electrons accelerated and heated? And I will come back to the corona idea when we are going to discuss the association of neutrinos from an AGN, which is a Seyfert galaxy without a jet. So just keep this in mind that when I'm going to talk about the corona, I'm going to talk about an arbitrary, for the moment, region very close to the black hole, where there is no strong jet. And here is what a blazar looks like. So an AGN with a jet. What do we typically observe? So on the left, you can see the spectral energy distribution of photons going from radio wavelengths to X-rays to GeV gamma rays, extending to TeV gamma rays. And you can see that it has this kind of nice two-component structure. And this is, let's say, very, very common among blazars. All blazars have this broad spectrum, more or less. Two broad components, non-thermal emission, which means that we need relativistic electrons or protons to produce this via non-thermal radiative processes. But you also see that the flux, especially in the X-rays and TeV gamma rays, is not constant over time. So the flux varies on many, many time scales. It may vary if you look here on the light curves in TeV gamma rays and X-rays over the course of 9 days within 15 minutes. So you can imagine that you observe this large-scale jet that we said before, and you detect gamma ray and X-ray emission varying on a scale of minutes. But then you can look the same object on a much longer baseline, going from 2009 to 2022, using Fermi in the gamma rays, GeV, and you can see over 14 years how the overall emission changes. Currently, we don't have a fundamental model for explaining the time variability that we see in blazars. Where we always try to, let's say, create a model that is going to explain a very specific time window in time, but we don't have a fundamental understanding of what drives the variability, because this comes from the jet. Why is the jet variable in AGN? So this is, again, an open question. And just to make things a little bit more complicated, blazars, as I said, they have this two-component spectrum, like one component and another one, but they do not always have the same characteristics. So there are blazars that they have relatively low gamma ray luminosity. These are called low-power AGN. You have the high gamma ray luminosity AGN, and you also see that there is a difference in the peak energy of the component. We believe that this kind of phenomenology is related to the environment of the jet. So there are these high luminosity AGN, like this one, that they are powered by radiatively efficient accretion disks. And they also have very, let's say, non-negligible radiation fields coming from clouds that they are illuminated by the accretion disk. So you can imagine that you have the jet propagating into a photon bath, which is of external source. So this has strong external photon fields. Whereas the low luminosity AGN, like this one, we think that they are powered by inefficient accretion flows. They have less powerful jets, and they do not have strong radiation fields external to the jet. And why is this important, you may ask, or I may ask, why do we really care about the presence or not of external photon fields in blazars? I mean, what do you think? I mean, what are the two basic processes for neutrino production in astrophysical environments that we have discussed? Photon field. Exactly. So we would like to explain neutrino production from AGN jets, so we will at least postulate that there are relativistic proton jets. These will interact with photon fields. So it's very important to know what is the radiation field in the vicinity of the relativistic proton population in order to make a robust neutrino estimation. And again, just to give you the theorist, let's say, perspective of an AGN jet, in order to give you an idea of what we don't really know, is that understanding the AGN jets and coming up with a fundamental model that describes the AGN physics coming from jet formation, particle acceleration, and radiation is an open question because it's really a tough problem to tackle. So we are talking about the formation of these plasma outflows from very close to the black hole. They extend to very large distances, up to 10 parsecs. We kind of have an idea of what is the topology of the magnetic fields, but we don't really know what are the instabilities of plasma that they trigger energy dissipation in these outflows. And we need energy dissipation because this means that there's going to be a mechanism that transfers energy from the bulk of the jet to the particles, and the particles will later on radiate, produce neutrinos and whatever. But we don't really know where the acceleration of particles takes place, if it is at 0.1 parsec, 0.01 parsec, 10 parsecs. What is the characteristic mechanism? Is it shock acceleration? Is it magnetic reconnection? Is it turbulence that accelerates the protons? And it's a multi-scale problem that we currently do not have the full picture. So what I'm going to tell you about neutrino predictions from AGN jets is going to be a very, let's say, naive picture because we don't really have the full understanding of the problem. So we are going to consider that somewhere in this multi-scale jet, protons are accelerated and they interact locally with some photon fields to create neutrinos. So how do we do this? If we want to model neutrino production in AGN jets, as we said, we need to account for all the non-thermal radiative processes that are important for explaining the photon fields coming from the jet. These include electron synchrotron radiation, Compton scattering, inverse Compton scattering, photon-photon pair creation, proton synchrotron radiation, proton-photon pair production, proton-photon pion production, and in certain cases, PP collisions. So we have to account for all of these processes in order to make a calculation of the photon and neutrino emission coming from the source. And what do we typically do? As I said, we go back to the spherical cow model. We consider a spherical region somewhere in the jet with some arbitrary conditions. Then we account for all the processes that I mentioned before. We specify the geometry. Okay, typically it's a blob or a slab. Then we solve the equations. I'm going to show you in the next slide what equations we solve in order to calculate the photon and neutrino emission in the rest frame of the blob of the jet. And then we have to apply Lorentz transformations in order to transform all the quantities from the rest frame of the jet to the observer's frame of the jet. Yeah. Yeah, so boundary conditions. I'm going to show you what type of equation we're solving, and I will get to that. Yeah, before that, just to give you a sense of the different flavor of models that we have when talking about AGN modeling. So you could explain, remember this two-component spectrum that we saw before, that all AGN jets have this two-component photon spectrum? Okay, the point is that as modelers, we want to have an idea of what is the first component, what is the origin of the first component, what is the origin of the second component, what is the mechanism that produces the second component. So here you can see schematically all the different flavors of models that we have at hand. The most common ones were, okay, the low energy component is coming from the synchrotron radiation of electrons and positrons in the jet. The high energy component is simply the inverse Compton scattered emission of this component. So these are purely leptonic models. They do not account for the presence of relativistic hadrons in the jet. You could have a similar model where the high energy component of the SED is because it's produced by the synchrotron radiation of protons. You could have more sophisticated or complex models where the gamma ray component here is produced by secondaries that are produced in the charged and pion decays. So electron-positron pairs that are produced from the pion chains. You could also have this kind of models, which are mostly leptonic, as you can see, but the contribution of all the secondary electron-positrons that are coming from the hadronic interactions in the source, they only have a subdominant contribution to the total photon spectrum. So we call these hybrid leptonic models, just to differentiate from the purely leptonic models. And for those interested, you can also check the literature where I included some of the seminal papers for each kind of scenario. What is the numerical approach that we use? We use a transport equation in the energy space. So we consider the distribution function for each particle species in terms of energy, and we want to evolve it as a function of time. So this is the typical type of equation we write for one particle species. You can identify here the escape term. So we consider this as our boundary, the spherical region, and we account for the probability of particles leaving the source on a given escape time scale. So this is a sink term, but we also have injection terms. Similarly to the equation that we saw when we discussed about the cascade formation in the atmosphere, remember in the second lecture, or first lecture. And this is the important also term where we have energy losses, and this is reminds of an advection term in fluid dynamics. So if you have seen fluid equations, this is an advection term. So here I have not introduced any diffusive term in terms of energy transport. Okay, so boundary conditions here do not come so much in play because we don't account for, we have just initial conditions and we have to consider how to set our boundary conditions in the energy grid of each distribution. So for example, because particles are losing energy, we consider that we have a zero net flux at the lower energy limit, or we set the number of particles at the lower energy limit to be equal to 0. But here we don't account for the spatial distribution of particles, so how they are distributed in space, which is kind of simple compared to cosmic ray propagation equations, you may think, but it's not like that, because when we want to account for all the different particle species, I mean, we do not have many. We have protons, we have neutrinos, electrons and positrons, it's here, photons and neutrons. The difference with respect to the propagation codes that you might be familiar is that here we have a coupling between the secondary particles that are being produced and the primary particles that are producing the secondaries. So if you start with a population of protons and electrons that are accelerated to some high energies, the protons might they might lose energy, because of photopion interactions, and they might produce, they will produce here electron-positron pairs through the decay of the pions. And these electron-positron pairs are added to the initial population, and this population is evolved in time. And because they lose energy because of synchrotron losses, because of inverse Compton scattering, this energy lost is going to be transferred into the photon population. So there is it is a multidimensional problem, which is nonlinear because there is a coupling between different particle distributions. And we have to really tackle this. If we account it also for the, let's say, how particle distributions are evolving in space, this would be even more complex. Cosmic ray propagation codes only account for the propagation of the primary particles, how they decay. They count the secondary populations as they are produced in different length scales, but that's it. They do not consider the emission coming from these secondary particles and how this may affect the primary distributions. So this was my supervisor's original code back in the 1990s. Fortran 77, thousands of lines. Nobody can understand anything from that code besides the three of us here. So, probably it's going to be deprecated as well because the libraries are not going to work anymore. So I asked my PhD student when he started, okay, Stamatis, could you write from scratch another code that can actually solve this problem in a more efficient way and also be usable by others? That was the point, and be much faster, right? Use another algorithm, numerical algorithm, to solve these equations in order to be faster. So Stamatis, I was very lucky because within a year, he actually managed to create this code. The difference with the previous one is that we do not account for some processes here, like we don't really care about that. And we don't have the neutrons, the neutron equation involved, but we have added proton-proton collisions in the game. Process that you can also download it. You can experiment with it. We're also going to you can also use it for MCMC fitting of different astrophysical sources. And we're also going to create another branch on GitHub, which is going to be even faster than the one that we have uploaded for proton-photon calculations. So just also to give you a sense that what we are doing in this community is that this code and the other code AM3, which is developed by a group in DESI, are the only public codes currently on the market that they can be used for multi-messenger modeling of astrophysical sources. And this is the first ever paper in our community, at least, where we kind of compare the systematics of different numerical codes that are being used, either private or public ones. So if you're interested to see how we compare different codes in an open, let's say, environment without criticism, because we were not colleagues before, we were, you may say, competitors, you can check this paper. On average, we have, let's say, 10 to 20% systematic uncertainties because of the way we tabulate some of the reaction rates, the way we solve the equations, and so on. So if you are interested, check that. So this brings me to the highlights. We've seen also in some of the student talks and in my talk earlier that these are the most, let's say, prominent neutrino point sources in the sky to date. This is the Blazar TXS that was associated with high-energy neutrino, and this is a Seyfert galaxy at very close distance to us. It doesn't have a radio jet. So immediately you see that we have potential neutrino associations with two types of AGN, a Blazar and a Seyfert galaxy, like one with a jet, powerful jet, another one with a non-powerful jet. So TXS, this kind of Blazar, you can see here the spectral energy distribution of that source at the time when this energetic neutrino was detected by IceCube. You can nicely see the first component that we discussed before. You can see the gamma ray component here, which is much brighter compared to the average gamma ray flux. And here you see the neutrino flux limit arising from the detection of this one neutrino. This is an interesting source because it has external radiation fields that are important for the modeling, as we said. We also have observational evidences of how high it is the accretion rate onto the supermassive black hole. We know how luminous is the disk, or we have a sense of the upper limit. So we know the environmental parameters, if you wish. So then we ask ourselves, how can we model this spectral energy distribution and at the same time account for the detection of one neutrino of that particular energy, which was 290 TeV, more or less? We have all the machinery now in place. We have the multi-messenger model that I described before. So what do you think would happen? I mean, back in the day, before this event, people thought, okay, this is leptonic of origin, and this could be hadronic in origin in order to explain also the very high energy neutrino flux. But in the end, different groups ended up with the same solution, that in order to explain the observed photon energy distribution and at the same time produce neutrinos in the specific energy range of that event, you cannot make it without assuming that the hadronic component, the hadronic electromagnetic component is subdominant, as you can see here. And all the rest of the electromagnetic radiation is attributed to processes of accelerated electrons in the jet. Okay, you might ask, why does this happen? We can show theoretically using these efficiency factors that I told you before, the opacity to gamma pair creation and so on. We can show analytically that the neutrino emission coming from this jet cannot exceed the X-ray luminosity, as you can see here. This is an inset in the X-ray spectrum, because if you increase more the neutrino luminosity coming from that source, you inevitably increase the X-ray luminosity, which comes from all the secondary particles that have been created in the source. So you cannot expect more than that. We also showed that this jet or this neutrino association implies that you do not have acceleration of protons to ultra-high energy cosmic rays. So it is not a 1-1 correlation. Let's say one source is an ultra-high energy cosmic ray accelerator and a TeV or PeV neutrino emitter. And we also found that the ratio of this neutrino to gamma ray luminosity is rather small. It's 3%. And this is an important number. Why? I will skip that because when we talk, this is one source, but when we want to explain or make predictions about the diffuse flux coming from all blazars across the universe, we need to come up with some way to formulate our problem. So in a sense, we know what is the distribution function of AGN in gamma rays over redshift. So if we have a way to, let's say, scale the neutrino luminosity of any given AGN to the gamma ray luminosity, then we can build a population model and see what is the diffuse neutrino flux from that. This is one of the early works that we did back in the day, where we assumed that this Y parameter, this ratio between neutrino to gamma rays, was ranging from 30% to 80%. This was back in 2016 with very few, not very sensitive upper limits. But more recent results by IceCube provided these sensitive upper limits at the extremely high energies, extremely anyway, 10 to the 16 and beyond. And you can see that because of that, we can constrain this Y parameter to be less than 10% for the blazar population, which is consistent with the values that we find by modeling individually the Texas source that was associated with at least that one neutrino event. Okay, one may say, but is this Y parameter, this ratio of neutrino to gamma ray luminosity, universal among all blazars in the universe? So there were different types of studies. One study was trying to address this question by asking, okay, let's make the hypothesis that the diffuse flux that we see in IceCube is attributed only to blazars. Okay, what do I need in order to be consistent also with stacking limits from AGN catalogs, AGN gamma ray catalogs? And they found that this Y parameter, which is shown here, should decrease with the gamma ray luminosity. So the most luminous gamma ray sources should be less efficient neutrino emitters. But this was a data-driven, let's say, result in a sense. The question is, can we answer this question quite differently? And I think yes, but we are starting now. Another approach is, instead of address this question like that, you can model individual blazars with different characteristics, different gamma ray luminosities, and try to compute from your theoretical model what is this Y parameter. And here I show you some examples. These are the estimates we have for Texas. These are some other previous blazars that we have modeled in the past. And you can see that on average, there is a trend of this Y parameter with gamma ray luminosity, a hint for a negative trend. I'm not saying this is the answer, but it is a way to move forward and then try to understand if the model tells us that the neutrino luminosity scales down, the neutrino to gamma ray luminosity scales down with gamma ray luminosity, Why is that? What is the physical difference between sources? Why is the proton, relativistic proton luminosity divided by the gamma ray luminosity, which we call baryon loading in our in our field? What is this baryon loading? Why does it decrease with gamma ray luminosity? What is the underlying physics behind that? So this is an open question still. Okay, we're actually trying to do this kind of analysis with a PhD student from Chemistry.net. She works on the extreme BLAC population, and results are underway. And I would like just to close this kind of lecture by giving you now another view of the other galaxy. So this is what we kind of do in the blazar business. We model the photon distributions. We have some predictions for the neutrinos. We try also to compare with diffuse flux measurements and so on. But what about NGC 1068, which is the other nearby Seyfert galaxy, one of the best studied in astrophysics because it's very nearby? Here you can see the full spectral energy distribution of that source. You can pay attention to this part where you can see the ice cube neutrino spectrum, which is rather steep. It has a slope of minus 3.2 or something. It's quite luminous in terms of luminosity. You can see it's of the order of 10 to the 43 ergs per second. But at the same time here, at the very high energies gamma rays, you see the upper limits by the MAGIC telescope. And this is very crucial for understanding where these neutrinos are coming from. They must be coming from a region which is opaque to gamma-gamma per creation. And why is that? Remember the previous lecture that I showed you the energy distributions of gamma rays coming from neutral pion decay and neutrinos coming from charged pion decays. And these were very similar. They differed by a factor of 2 in energy, more or less. So this means that this means that the source that emits these neutrinos will also emit TeV gamma rays of similar energies and similar flux, but we don't see them. Why? Because they are attenuated inside the source. So immediately we kind of know that the neutrino production site must be compact, have high density of photons in order to attenuate the TeV photons that are co-produced with the neutrinos. What actually attenuates these TeV gamma ray photons that we don't see? The X-ray photons of the corona. Remember again that I told you the corona has this very nice power law spectrum in the X-rays. This is the X-ray spectrum of this AGN, and this is responsible for the attenuation of the gamma ray photons. So Kota Murase and others have actually produced many papers about this topic, but all actually agree on this point that you need a compact corona of the order of tens of gravitational radii of the black hole. Okay. Now, since this discovery, there have been many, many models. Pick your flavor. So here I just present you a couple. And the models, they have different hypotheses, mostly about how protons are accelerated in the coronal region of this AGN. Others are very generic. They do not specify the mechanism, so they're pretty flexible. Others consider acceleration of particles in turbulent accretion flows, which is part of the corona. Others discuss diffuse shock acceleration in the accretion flow. Others, like me and Damiano and collaborators, we are invoking magnetic reconnection. Common findings, as I said, the corona is compact. It has a small size. It is opaque to gamma rays. The GV gamma rays that you see here are not coming from the same region as the neutrinos. So these must have another origin, most likely leptonic, because of the starburst character of this AGN. You can ask me more about that later. But depending on your model, you have very different findings about the physical properties of the corona. And this is a very nice way of how we can also use neutrino observations of high energies to learn more about the physical properties of environments that we cannot otherwise see. So depending, we could have a plasma which is dominated by pairs, or we could have a corona which is equally dominated by protons and electrons, or how magnetized is the corona. All of these physical properties are different depending on your model you choose. So in the next couple of minutes, I simply want to illustrate how we can start from a simple model about one source again. And if we believe this model is true, what predictions we can make again about the population of AGN Seyferts. So in our view of what is the corona in this source, in this AGN, is that close to the black hole, we might have the formation of a current sheet where reconnection takes place and accelerate particles. These particles, the leptons that are accelerated, they comptonize photons that are coming from the disk, and they produce the X-rays coming from the corona. At the same time, the protons that are accelerated in these current sheets, they are responsible for the neutrino production. So the basic ingredients of our model are rather simple. The main source of energy in our system is electromagnetic in nature. So we have conversion of electromagnetic energy into X-ray photons and relativistic protons. So both X-ray luminosity and proton luminosity, which are the two key parameters, are related to each other. You see, the protons cannot have much higher luminosity than the X-ray luminosity, which is an observable in our case. So this is pretty nice because we can constrain our model. We cannot arbitrarily say that the protons in the corona carry a luminosity which is 100 times greater than the X-ray one, simply because they share the same kind of origin in terms of energization. Okay, then.
Yeah, this is the accretion disk that you show here horizontally, or is this some jet structure?
Okay, yeah, so the accretion disk is all this structure, and this is a stream of plasma that manages to reach to the black hole, because on average, the accretion flow is terminated here because of very strong magnetic pressure. So the magnetic pressure is so high that it stops the gas accretion onto the black hole. And this is a very dynamic kind of process. It's not a stationary situation. This can be destroyed and revived and so on. By the way, this is a 3D GRMHD simulation that does not account for particle, the kinetic of particle, the kinetic physics of particles. It's just fluids, GR, and electromagnetic fields. So we have these two components. We assume that the X-ray corona has a simple power law spectrum, which is what we typically see from these sources. And then we put these ingredients together. We assume that the protons interact with the X-ray photons because of P-gamma interactions, and we can compute our neutrino spectrum. And notice the only free parameter here is basically what we are going to see later. It's basically this parameter here. I mean, I will say it now. It's the characteristic energy of the proton. So let me describe a little bit first the proton spectrum. So another ingredient that we need besides the total luminosity of the population is what is the energy spectrum of the protons that they are going to produce the neutrinos. And this is kind of motivated by simulations again in magnetic reconnection, that the proton spectrum is very hard. It peaks at a characteristic energy, which we call a break energy, and then it becomes steeper. How much steeper, we don't really know yet. So this characteristic energy is related to how strong is the magnetization in that corona. Higher magnetization, which means higher energy density in the magnetic fields, means that the protons on average will gain higher energy, and thereby this value scales with sigma p, which is the magnetization. But this is the key free parameter, which is coming from the microphysics of the corona that we don't really know. And here, if you plug in the result, if you try to make the calculation for the neutrino spectrum for NGC 1068, the results are the orange spectra that you can see here, which are in, let's say, in the correct energy range, roughly correct the scale in luminosity. And again, we can infer some of the properties of the corona. But this was one source of a given X-ray luminosity and a given black hole mass. So how can we take this model and extrapolate it to the diffuse, to the population of Seyfert galaxies that span a wide range in X-ray luminosities from 10 to the 42 up to 10 to the 45, and black hole masses that can also range from 10 to the 6 point something up to 10 to the 9 solar masses. For that, I asked my other PhD student to work it out. So what we did, what Despina did, is that she tried to make a parametric study of the neutrino spectrum coming from this model. And as you can see, for example, if you change the magnetization of the corona, which is the color here, how the neutrino spectrum changes. And you can see that as you increase the magnetization, you increase the peak energy of the neutrinos. Why is that? Yes, because as we saw a little before, this sigma p, this magnetization, determines also the energy of the protons that are producing the neutrinos. So more energetic protons, they produce more energetic neutrinos. And also more energetic protons, they carry also higher luminosity, which is later on transferred to neutrinos. So you also affect the efficiency of neutrino production. This F parameter that I discussed before, this efficiency factor changes with sigma p. And she parameterized that, and actually she showed analytically that here, analytically and numerically, that the neutrino to X-ray luminosity, which is a measure of the efficiency, let's say, so how much energy is transferred into neutrinos compared to the X-rays, is a function of sigma p. So these points here are obtained for a higher sigma p compared to those, but also it depends on the ratio of the X-ray luminosity of the corona and the black hole mass, or the so-called Eddington ratio. It is the X-ray luminosity divided by the Eddington luminosity of the corona. Probably you know about the Eddington. If not, we can discuss it later on. But the point is that now we don't have three independent parameters like Lx, the black hole mass, and sigma p. We only have two, the Eddington ratio and sigma p. And the Eddington ratio is something that we kind of measure, or we know from observations of AGN. We measure the X-ray luminosity, we can estimate the black hole mass. So essentially, you build a one-parametric model, if you can imagine that, which is pretty amazing, in my opinion, just to have a one-parametric model that you can test with observations. So here are some preliminary results where we took the Swift Bat 70-month catalog of bright AGN, X-ray AGN. These are nearby sources, so this axis shows the luminosity distance of the sources. So they go up to 100 megaparsecs. And the other blob here of points are simulated AGN from another catalog. It's a mock catalog, it's not a real catalog, that extends up to redshift of 4. And actually, we combine these two, let's say, samples in order to make a calculation for the diffuse now flux of neutrinos based on this model. As I said again, here the only parameter which is unknown is the magnetization of the corona. All the other X-ray luminosity, black hole masses are known. So if you do this calculation, assuming for simplicity now that all coronae have the same sigma p, the same magnetization, you end up with this spectrum. So here you can see with black dashed line for comparison the contribution of NGC 1068 in neutrinos. Here is the diffuse flux calculation coming from our analysis. And it's pretty interesting, I mean, that it has the same kind of shape with the NGC 1068, because in our model, the neutrino shape is determined by the efficiency. And the efficiency is something that it depends on the Eddington ratio. So everything is interconnected. Plus, something that I didn't talk about, in our models, the magnetic fields in the corona are very strong, so of the order of kilogauss and higher, which means that the charged pions that are being produced, they might lose their energy faster before decaying because of synchrotron losses. So if you account for this synchrotron cooling loss term in the pions, you decrease the flux of neutrinos you produce above a given energy. So this is just a schematic just to show you the suppression we expect to have in the neutrino spectrum because of that. And we are actually doing the calculations now numerically accounting for this effect for every source in the sample. We have 1 million simulated AGN. And just to put things in perspective, and I'm closing with that, I mean, to me, when I started working on modeling of AGN and blazars, I was very, impressed when we started making some predictions about the blazar contribution at very high energies by IceCube. And then people were saying, okay, and what produces the lower energy neutrinos? And to me, it was like looking in a very narrow window in energy space. When you look the diffuse flux of neutrinos, you only have a narrow window, but you have so many possibilities of potential sources contributing to that energy range. But to me, it was like, I couldn't think of another plausible scenario. So the most plausible scenario to me, and now it's coming into appearance, is that you have blazars contributing to the highest energies, and you have another population of non-jetted AGN that contributes to the lower energy part of the spectrum. So you have this nice superposition. And I think that, at least in our model, is something that you can easily test because it is essentially a one-parametric model. So I hope that I gave you an idea of how we use some basic ingredients in our modeling and how we use multi-messenger observations in order also to understand a little bit better what happens in these types of sources in terms of physics. And closing with these multi-messenger pictures of diffuse fluxes, we have the diffuse flux from IceCube neutrinos, the diffuse gamma ray, the extragalactic or isotropic gamma ray background by Fermi detected in G in gamma rays, and also the ultra high energy and high energy cosmic ray component. Whether or not these are related or associated to the same kind of sources, I think it's pretty safe to say that the sources that contribute here to the spectrum are not the ones that are producing the neutrinos, but it is still a question that people in our community are trying to understand. So thank you for your attention, and thank you for also giving me the opportunity to speak here.
So this picture is nicely now coming together with all the AGNs with their different flavors.
Yes.
Filling in the spectrum. Yeah. So
Yep.
this is, yeah, we also have some interesting results concerning Seyfert galaxies from IceCube. So we see now some 3 sigma correlations from point sources, like the catalogs of sources. Yeah. So at ICRC there will be some results on that. Nice. Yeah. Are there any questions? So this was Maria's last lecture.
Yeah.
So now would be the time to ask final questions. But you are also here tomorrow, yes, right? Okay. Yeah.
And in the discussion session.
And the discussion session today. Yeah.
Thank you for the lecture. So when you show the gamma ray spectrum measured at the AGN, not just gamma ray, but also extends to X-ray and so on, are they measured at the same part of the AGN, or you can measure the spectrum at different sections of the source? And yeah.
Okay, for example, you mean here where we have X-rays and gamma rays, we know if we can identify where they're coming from?
Yeah.
The short answer is no, because we don't have the resolution, angular resolution for any of the instruments currently to identify sizes that are smaller than a parsec. it might be possible for kiloparsec scale jets from AGN with the Chandra telescope to identify knots, but on kiloparsec scales. So currently we don't really know, because we cannot have the angular resolution to image the source, where the gamma rays are coming from, the X-rays, and so on.
Okay, so I guess if we would be able to resolve like the jet parts, that could answer the question of where the protons are accelerated, or like particles are accelerated in general. Like,
yeah, I don't know. I mean, definitely it would help. Like if we had the analog of microquasar jets in our galaxy, like, and have an imaging of how the spectral index of the emission changes with distance, it might be helpful. But this is something that, as far as I know, cannot be done on sub-parsec scales, which is the most crucial part, because all of this emission is very, very variable, which means that it must be coming from the small scale jet, not the large scale jet.
yes, okay, thank you.
You said tens of Schwarzschild radii in order to absorb the gamma ray emission.
Yeah, this was for NGC 1068. Yeah. But for this kind of, for the blazar, because we have the TeV gamma rays there by magic, you can also play this game and see how far away from the external photon field or the black hole the source must be. And we set an upper limit. The distance should be close to 0.1 parsec from the central black hole, which is bigger compared to NGC 1068, because you don't have such strong attenuation.
Okay, one question there.
Yeah, I wanted to ask, because I mean the Corona models always use very high magnetic fields.
So I cannot hear you. So.
I was saying that the Corona models always use very high magnetic fields. Do we have any constraints from like GRMHD simulations on the magnetic fields of the Corona, or?
No, actually, GRMHD simulations, if I'm not mistaken, they assume some strength of the magnetic field. So it's not like something that comes out naturally. Plus, if you compare the energy densities of these strong fields with the gas density or the radiation energy density, they're kind of comparable. So it's not like you are very far from equipartition. For example, in M87, which is a nearby radio galaxy, and we have imaged the black hole, there are some estimates of the magnetic field. And also there are some upper limits, because you also have Faraday rotation effects. And you can set an upper limit on the line of sight magnetic field component. So this is of the order of a few hundreds of Gauss. So.
Okay, thank you.
Okay, I think now's a good time for lunch. But before we have lunch, let's have a big round of applause for Maria.